So let's see how do we go about that. So the intuition is that we want to decay the learning rate in proportion to the update history, right? So for the features which are getting a lot of updates, so I have a very dense feature, so the derivatives are large, and I updated it in the first step by a large value, second step by a large value, third step by a large value. So I'm doing reasonable updates for this. So maybe now I need to be a bit conservative and decay the learning rate. But if there was feature which is very sparse, got a very small update in the first iteration because the total gradient that I computed was very small, again a small update in the second pass, again a small update in the third pass, then I need to let the learning rate be high, right? Because I'm getting small updates, so let me at least move a bit aggressively in those update directions, right? So that's what kind of is the intuition behind the update rule for AdaGrad. What I'm going to do is I'm going to maintain the history of the updates that I'm making, right? Okay, so now let me try to explain what is happening here. So now I'm taking a running sum of the history of the updates, right? So this delta WT tells me what was the update that I've made or what was my gradients, right? And this is a running sum. At every time step, I'm adding the current derivative and the square of it, right? So I'm just taking the squared derivative and keeping it as the history. So it tells me the magnitude of the updates that I have done so far. And then what I'm doing is I'm taking the learning rate and I'm dividing it by this history. So what will happen is if they have a feature which is very dense and which has got a lot of updates, then this history keeps increasing, right? Because you are making large updates at every time step. At time step 0, you made an update, time step 1, you made an update, time step 2, you made an update, and all of this is getting added here. And all of these were large quantities because this was, say, a dense feature, right? Then your VT after a few iterations will grow and the learning rate would appropriately shrink, right? But if this was a sparse feature, then across iterations, maybe even when I reach t equal to 100, nothing much has been accumulated here, right? Because all these updates were very, very small because this was a sparse feature. So hence my VT has not grown much, and hence my learning rate will not decrease aggressively, right? So now the learning rate has become proportional, or rather inversely proportional to my update history. If I made large updates, then I decrease the learning rate aggressively. If I made only a few updates, I don't decrease it aggressively, right? So that's what is happening here. So just as you have the update equations for W, you can also have the update equations for B, right? Okay. So this is the algorithm. From now on, I'll not spend too much time on the code, right? It's just a modification of the codes that you have seen so far. So in this place here, this is where I'm accumulating the history, right? I'm just taking the previous update plus the current update square, right? That's what the equation said. And then my learning rate here is going to be divided by this update, right? So now I think these are small code snippets which you are comfortable with, and you can take the equation and write the code for that, right? So to see this in action, right, we need to first create some data where one of the features is sparse, right? And I also remember that I can only show you a 2D plot. That means I can have one feature on the one axis and another feature on the other axis. So I'm just going to be able to work with two features. One of them is going to be W and the other one is going to be B, right? And remember, the feature B or the feature corresponding to B is dense because it's always on, right? The corresponding input is always 1. So I can't do much about that. So what I'm going to do is that I'm going to create a data where my X, which corresponds to W, is going to be very sparse, right? So that's how I'm going to create this data. So let's see, this is what I'm going to do. So this is what I'm saying, right? The third bullet point here says that we just have two parameters W and B. Of these, the input feature corresponding to B is always on. So we can't really make it sparse. So the only option is to make X sparse. So the way I've created the data for this is that I created some random 500 random X comma Y pairs, and then for roughly 80% of these pairs, I set X to 0, right? And thereby making the feature X very sparse, because 80% of the times it is 0, and that's the definition of a sparse feature, that a majority of times, or significantly more than a majority of times, it's 0. So that's how I created this training data. And then so I took that data and I ran the gradient descent, momentum based gradient descent, and Nesterov accelerated gradient descent algorithm on that, using that data. And The loss surface was something like this, right? I'm showing the 2D loss surface, but let's try to understand, let's try to make a commentary on it and try to see what it actually is, right? So as you know, this red means high. So these are the regions here where the loss is a bit high, and also in those regions you see that there's a slightly larger difference between consecutive contour lines. That means they are a bit flat region, right? And this region is blue here, okay? So that means in that region the loss is very low, and also from going from here to here as we go down, let me just change the color, going from here to here as we go down, the slope is very steep, and that is obvious because the difference between two consecutive contour lines is now very small, right? So then this is essentially a surface like this, which is peaking at the two red portions, and then it's going into a valley, which is the blue valley, and it's going steeply into the valley, right? That's why you see this steep slopes here where the difference between two consecutive contour lines is very small, right? So that's what the loss surface looks like. Now I ran gradient descent. I started from some point. I started all the three algorithms from the same point, right? And I started gradient descent, momentum based gradient descent and Nestra, right? And there, as I would like to say, let me just go back to the slides. Uh, so there's something interesting that is these three algorithms are doing, right? And can you spot it is the question, right? So what exactly is happening here? And remember that I should have mentioned that my horizontal axis is the W axis and my vertical axis is the B axis, as has been appropriately labeled on the plot, right? Now with that information, can you tell me what peculiar behavior is happening here? Okay, good. So what you're saying is this, right? That I mean, as I say, it looks like these algorithms went to a school where no one taught them gradient descent or no one taught them Pythagoras theorem, right? So what I mean by that is, if you look here, initially all the three algorithms are moving in the direction of B, right? They are not, they have moved only till this point, right? Till this here, they have moved only little bit in the direction of W, right? So till this point is where they have reached. So they have not much moved from the initial value of W, right? But where they have moved a lot in the direction of B, right? And that is expected because B was the dense feature, hence its gradients were larger, and hence you were making larger movements in the direction of B. Whereas W was the sparse feature, intentionally made sparse as explained on the previous slide. So the gradients for W were smaller, and hence you were making smaller movements in the direction of W, right? And after you reach the valley, then the algorithms realize that now there is no more value in moving in the direction of B, right? Anyways, the gradients there are becoming smaller now because you have reached the steep region, and then it slowly starts moving very, very slow steps in the direction of W, because there again the gradients are small. What can you do? But then it still moves in that direction, and then it reaches the minima, right? So it takes a right angled path, right? Whereas ideally you would have wanted something which just directly travels like this, which would mean that it is making proportionate movements in both the direction. Even though the derivatives in the direction of W are small, you are still able to somehow jack up the learning rate so that you are able to make proportionate movements there and then reach the minima faster, or at least like a more appropriate route, right? So that's what is going wrong with these algorithms, three algorithms that we've seen in the last lecture. So all the algorithms are moving in the vertical axis and then they start moving along the W axis, and we know the reason for this. We already explained, I just explained what the reason was. And such sparsity, right, it is very common in large neural networks, right? You have thousands of input features and many of them might be sparse, right? So there's not something like a toy example that I've created. This is going to happen in many neural networks, and hence you need to address this issue, right? That if you have sparse features, can you still make faster movements in those directions, right? So now let's see what AdaGrad does for this case, okay? Okay, let me just play this. So as you can see, right, AdaGrad is moving in the W direction also, right? Why is that happening? Because the learning rate for W, because our denominator is going to be small, our square root of Vt is going to be small, right? And if it's a quantity which is less than 1, then the denominator is, you are dividing eta by a quantity which is less than 1. So hence eta increases, and hence your updates in that direction increase, and hence unlike the other algorithms, you are proportionately moving in the direction of W also, right? Of course, here still the momentum based algorithm was faster, because momentum of course has its advantage, right? It makes mistakes, but it still reaches the minima faster. So let me just play that again. You can see that the momentum based algorithms, both Nestrov and all, they reached faster, right? But compared to gradient descent, AdaGrad was able to move faster, right? And there is still scope to improve AdaGrad because it does not have a momentum term. If I had added a momentum term, then I could combine the advantages of momentum as well as this adaptive learning rate, and we'll probably get in that direction at some point, right? We'll get in that direction, meaning we'll get towards such an algorithm at some point, right? But for now, you see the advantage that I'm able to move proportionately. Even though my derivatives are small, I have adaptively changed the learning rate, eta divided by the history of the updates, and that is allowing me to do that, right? So remember, my effective learning rate is eta divided by square root of Vt plus epsilon, right? And let me just ignore epsilon for now. So it's divided by the square root of Vt, and for W, this Vt is going to be very small because I'm not getting large derivatives there. Hence, eta is getting divided by a very small quantity, and if that quantity is less than 1, then effectively this learning rate is increasing, right? And that's what is pushing the derivative there, right? And I'll just explain this in more detail on the next slide. Yeah, but one disadvantage that, not disadvantage, but one thing I want you to notice, and I'll just play this again if required, is that as AdaGrad starts reaching the minima, just observe from now on, yeah. So it's slowing down quite a bit, right? And what is happening is that by this time, despite the smaller derivatives of in the direction of W, by this time you have accumulated some history. And now this effective learning rate is starting to slow down because it is getting divided by this accumulated history, and by that time that history has increased, right? So as it comes close to the convergence, not necessarily close to convergence, after a certain number of iterations, when the history is becoming large, then AdaGrad is slowing down, right? So that's one observation I'm making on this slide, and we'll come back to see if we can somehow solve that problem. Okay, so now let's examine this a bit more closely. So you remember that we are accumulating this history. Now V0 is delta W0 square, V1 is delta W0 square plus delta W1 square, and so on, right? So this is constantly growing. Vt is constantly growing uninhibitedly because you are adding those derivatives, right? And our derivative is proportional to x. That means for the feature which is sparse, these derivatives would be small. So then our history will accumulate slowly, hence this effective learning rate will decay slowly. And it's also possible that initially it increases because our denominator might be less than 1, so the effective learning rate increases, and even when it decreases, it is slow to decrease, right? Because your accumulations may happen only after a large number of iterations such that the denominator becomes large, and then the effect of slowing down kicks in, right? But as opposed to this, for a dense feature, what would happen is you had the B feature, which was the dense feature. Now this history is accumulating faster, right? Because now the derivatives are going to be non-zero always, right? Because this is like an always on feature. So your history is accumulating fast. It will not be zero for most of the time steps. And therefore, what will happen is Vt will start growing rapidly, and hence this will start decaying rapidly. Right. So now effectively what will happen is this advantage that you had, that you quickly moved in the direction of B and came to where you wanted to be, that will not happen, right? Because now this directions, the increments in the vertical direction will happen a bit slowly as opposed to earlier where it was quickly moving in the vertical direction. Now you are moving a bit slowly in the vertical direction because of this effective learning rate decaying as you keep making updates, right? So that's what is happening in this algorithm. Okay, and we can now see that visually. So here dw, let me just annotate the plot a bit. So here dw is essentially this delta w that I have, and Vt is the history that is getting accumulated for the weight w, and eta t is the learning rate for the weight w, right? So now what is happening, let me just show you things here, right? So as I had said, right, the Vt will keep increasing, right, because it's accumulating the gradients. Of course, at some point when you reach close to the minima and your delta W becomes 0, then there's no more additions happening, right? So that's why this will saturate here in this region, right? And that you can see here, if you look at the derivative, right, in that region the derivatives have now almost become 0, and hence no additions are happening to the history, right? No large additions are happening to the history. It was very close to 0, so some small additions are happening, but it's not reflecting in the plot, right? And looking at this also, so initially remember that the way your plot was, and this itself is interesting, and we should try to look at it in the context of the loss plot that we had, right? How is the derivative changing? So I'll make some comments. I'll go back to the loss plot and I'll make some comments there and then come back here. Yes, yes. On the x-axis you have the number of iterations, right? Yeah. So if I look at the loss plot, right, and let me just clear this and then make some comments here. Yeah. So remember we had started from here, okay? So initially the you are in a slightly, it's steep, right? From the beginning it's steep, right? But the steepness is increasing. That means as I keep going down, my derivatives will become larger and larger, right, in magnitude. The direction may be positive or negative, but the magnitude will keep increasing. Then when I enter this valley region, my derivatives will start becoming smaller again, right? Until they reach a point where the derivatives will become close to 0, right? So remember, initially they'll increase because I'm going down the slope and the slope is increasing. So the derivatives will increase. And I'm showing it this way because they're increasing in the negative direction, right? So the slope here is negative. So this is what the curve is like. So here the slope at this point, it's negative, right? Because you're going down. As you are going down or as you are moving in the x direction, the value of y is decreasing, right? Or as, so that's why the slope is going to be negative. So it's going to increase in the negative direction. Then again, it's going to start decreasing and then it will come to 0, right? And that's exactly what is happening in the derivative plot that we just saw. Now let me go back to the plot. Yeah. So this is what is happening, right? So initially here your derivatives, as you keep going down, it keeps increasing in magnitude, right? I mean, remember that you are increasing on the negative side, which is fine. Its magnitude is increasing. And then at some point, because here I'm going to take the square, that's why I'm talking about the magnitude, right? And then when it comes close to the minima, it again starts decreasing in magnitude and then it comes to 0, right? And that's because the loss surface was like that, right? So this is how the history is getting accumulated. This is how the derivatives are changing. And this is what is happening. The red curve tells you what is happening to the effective learning rate. As your history is accumulating, the learning rate keeps decreasing exponentially, right? So if I were to just plot, let's just see. This is what the learning rate curve looks like, right? The same plot I have plotted separately. So the red curve I have plotted in a new plot so that I can have more range on the y-axis. So the y-axis tells you the learning rate and the x-axis is the number of iterations. As the number of iterations keeps increasing, the learning rate keeps decreasing exponentially, right? So here it's continuously decreasing, okay. And here, for example, in the first step, the learning rate was 0.72 because I had initialized eta to 0.1 and then the denominator turned out to be 0.01 because V0 turned out to be something which led to this 0.019, and then my learning rate initially was 0.72, but as I kept going down, it decreased exponentially, right? So the main thing here to show is that I had kept my learning rate, initially learning rate as 0.1, but it became 0.72, right? Because initially my history was not large and hence the learning rate increased and then it started decreasing again, and that's exactly what we wanted. Initially it could be high and then it starts decreasing, okay? And the same argument for B also. So here for so the same argument for B, so the derivatives, so here the scale is a bit different, right? The derivatives are on the x-axis you have 2000, 4000, sorry 20,000, 40,000, 60,000. That's why you're not able to see the DWs here carefully. So that again the same behavior happens, your gradients change as you go along, and the history keeps getting accumulated. So the only thing I need you to focus on in this plot is that your history is constantly increasing, and as your history is increasing, here your learning rate is decaying even more faster, right? So here notice that the learning rate starts off itself with a very small value, which is 0.010, right? And again I had initialized the learning rate to the same value, right? So here again, so here see, remember the learning rate was 0.1, but your initial gradients were high because B is a very dense feature. So your V0 itself was 84.45, right? And since that was high, your initial learning rate itself was small, and hence you are moving less aggressive in the direction of B as compared to gradient descent and Nesterov and momentum, right? And that's why, right, these gradients are also getting accumulated very quickly. It's already 84, this history, right? The blue curve that you see already starts off at 84 and it keeps growing from there on, right? That's why it reaches very high digits, right? It reaches 5-digit numbers, and that's why your learning rate gets killed off aggressively, right? Because your denominator has now become 5-digit number, right? The square root of a 5-digit number. Okay, and that's again in line with what the intuition that we had, right? So these plots are again an explanation of everything that we saw, right? We're just seeing how the learning rate is changing, how the gradients are accumulating aggressively in the case of B, and hence the learning rate is decreasing aggressively, right? And the main point is that in B, the learning rate started off itself with 0.010 and then kept decreasing from there. Whereas for W, the learning rate started off with 0.72, which was higher than the eta which I had said, and then started out decreasing from there. And that's exactly what we wanted, because W is a sparse feature. So let the learning rate be higher and then let it decay as the gradients accumulate. B is a dense feature, so let the learning rate be small, because anyways you're going to get large gradients there, right? So that adaptive behavior has been seen here, right? Okay. Yeah. Now one more thing to note is that even though as you come close to the minima, right, as you come close to the minima, your derivatives have become zero. Even here you can't see them also because the scale here is very large. So the derivatives have become zero. That means these quantities, right? That means these quantities have become zero, right? But your history does not become zero, and that makes sense, right? Because it's a running sum. You're continuously summing it up. So even if the new terms that are getting added are zero, you still have the previous terms which you had accumulated in the sum. So your history will going to be remain large only, right? So that's what is happening here. And that could cause problems, right? And that exactly what is causing problems near the minima when your gradients are becoming small, right? But your history is still large, and hence your effective learning rate is small. So now the gradients are small, the effective learning rate is small, and hence when you're close to the minima or close in these flat regions, you're not able to move fast, right? Because you're not getting rid of this accumulated history that you have, and we need to see if we can do something about that, right? So let's just look at that. Is it clear what I just said? Okay. So now by using a parameter specific learning rate, we have ensured that despite W being sparse, we are still being able to move in that direction. And also we have ensured that B is undergoing a lot of updates, but its effective learning rate is decreasing. And there is this something which is to ponder about, which is not theoretically justified. Now you could imagine that in the denominator, I could have had eta divided by Vt as opposed to square root of Vt, right? I would have got the same effect, that my learning rate is inversely proportional. The effective learning rate is inversely proportional to the accumulated history, right? But if you replace square root by just Vt, then this algorithm does not work so well. And at least my guess is one of the reasons for that is that if you don't take the square root, then these quantities become very large very quickly, right? And maybe that kills off the learning rate in an unfavorable way, right? But there's no clear theoretical justification that I have seen. What's the flip side? While we got an adaptive learning rate for W and B, the flip side is that over time, the effective learning rate for B became so small that it was having a difficulty in moving in the W direction, in the B direction, right? So you see that now I was able to reach the right value of W, right? I was able to reach the right value of W. That's the right value of W because my minima is also here, right? So I'm in line with the right value of W, but I took longer time to find the right value of B, as opposed to the other algorithms which found the right value of B first and then took a longer time to find the right value of W, right? And this is happening because the history for B has accumulated and the updates in B are now very, very small. And we saw that in the plots where on the x-axis, on the y-axis, you had very large numbers which indicated a large amount of history has been accumulated. So the question now is, can we avoid this?